is my resubmission for Pset 0, and this part of the video is going to be focusing on part 1C, which is the proof by contradiction. And I initially started correctly. I initially started with my assumption that vertex V is the vertex that minimizes phi of V. That is completely fine. And also in the proof we're trying to prove, essentially, it boils down to the fact that phi of V is less than or equal to n over 2. So for our contradiction, we want to assume, for the sake of contradiction, we want to assume the opposite. So we want to assume that phi of V is greater than n over 2. I did not do that in my proof of contradiction. And that was a mistake, because you want to prove the opposite of you want your contradiction to be the opposite of the claim you're trying to prove for a proof by contradiction. And also later on in my proof, I sort of was hand wavy with my proof and didn't prove the claim rigorously. So I learned that was a mistake, but now I understand why phi of V must be less than or equal to n over 2. And we do that first by sort of assigning names to the subtrees that result from removing V. We're going to assign them the names A, B, and C. And any one of these could be of size 0, and that is completely fine. And without loss of generality, we can assume that subtree A is the size of subtree A is phi of V. And we can assume this because they're all sort of indistinguishable from one another. Now that we have this assumption, we can also use our contradiction assumption, the fact that phi of V is greater than n over 2. That essentially just means that phi of V is less than or equal to n over 2 plus 1. So that means that the size of A, our subtree A, must be less than or equal to n over 2 plus 1. And we can use this to set an upper bound for the subtrees B, and C, for the size of them. Because we know that this entire tree is of size n, and if the subtree A is at least of size n over 2 plus 1, that means that subtrees B and C combined, their sizes must be strictly less than n over 2. Okay, now we can apply the proof from part 1B, where we remove vertex V star instead of vertex V. This results in the subtree A being broken up into two subtrees. We'll call them A prime and B prime. And either one of these could still be 0, so that is completely fine. B of size 0, that is fine. And the third subtree, the subtree with V, we're going to call it V star. Now, we know that from our proof from 1B that A prime and B prime must be less than the size of A. And we also know, since we're assuming that the size of A is n over 2 plus 1, is at least n over 2 of size n over 2 plus 1, we also know that C prime must be less than n over 2, must be strictly less than n over 2. And this produces a contradiction, because we've shown that all the subtrees that result from removing V star are smaller than phi of V. But this contradicts our initial assumption that phi of V was the that vertex V was the vertex that when you remove it produces the smallest possible phi of V. So that must mean that our initial assumption that that phi of V is greater than n over 2 was incorrect, because we've just shown that you can have smaller subtrees created when you remove a vertex. So that was really the point that I missed. I was very hand wavy with my proof at first, and I was not rigorous in using the fact that phi of V is at least n over 2 plus 1, and using that to prove that you could arise a contradiction. The next part of this video is going to be focusing on part 1D. And for part 1D, I had two errors. The first one arose in my programming portion, And when I submitted to Gradescope, I kept getting the error, none type does not have the attribute r.left. Why was I getting this error? It's because I was neglecting to handle the edge case where r.left did not exist. This is a pretty big oversight on my part. Now, I've learned that I should consider all possible edge cases, no matter how unlikely they may seem. The second error that I had in my video, in my response to 1D, was the fact that, was in my runtime analysis. My initial analysis was that you're searching through all the nodes, but the algorithm stops halfway through. And when you do the math, you'll see that the number of nodes for a binary tree of height h, it's 2h minus 1. And I sort of did the math and showed that that resulted in a time complexity of big O of h. But that is incorrect. My analysis should have focused on the fact that my algorithm only searches one subtree at a time. Excuse me. My algorithm only searches one child at a time. This is important because if you only ever search one child at a time, even if you reach the end of the binary tree, you would have searched a maximum of h children. Okay, but each time you search a child, you're doing a certain number of basic operations, and these basic operations are constant time. So each time you search a child, you have you execute basic operations that will take, let's say, k, some constant k number of steps. So that results in our time complexity of big O of k times h. But again, time complexity is only concerned with n behavior. Basically, as your input goes to infinity, what is the behavior of your function? And k is some sort of constant, which does not affect n behavior. So big O, so we can drop it in our big O analysis. So it ends up being big O of h. Again, because you only search one child at a time, and you're performing a constant number of operations or comparisons each time you search a child. So what I learned from this is that I need to be more careful in my analysis of the algorithm itself. Okay, to summarize everything I learned from my two resubmitted questions, for part 1C, I learned that I need to be absolutely rigorous with my proofs. I was very hand-wavy with my initial proof, and that simply is not going to hold up. Proofs require rigorous sort of mathematical or some sort of demonstration that the claim is true, not some sort of this is obvious sort of response. For part 1D, I learned two things. Number one, that I must consider all possible edge cases, regardless of how unlikely they may seem, when implementing my code. And the third thing that I learned is that when analyzing my runtime, I want to go step by step through my algorithm to make sure that my runtime analysis actually applies to my algorithm. Because my initial runtime analysis was just wrong, and it also just didn't match my algorithm. So I want to be careful and thorough with my runtime analysis by going step by step through my implementation. And I will implement these in future Psets.